Hello everyone, this is Jose Maria Martín-Olalla speaking. I am professor of physics at the University of Seville in Spain. My first language is not English, so I apologize for any inconvenience during this talk. I am going to present a manuscript study published in the European Physical Journal Plus on June 13, this in 2025, presenting a proof of the Nernst theorem. The Nernst theorem was formulated in 1905 and it was proven by Nernst in 1912. In the following year, Albert Einstein refuted the proof, and since then the theorem is known as the third law of thermodynamics, or it is considered an independent postulate, a postulate independent from the second law of thermodynamics. In the study, I present a proof, I think convincing and simple and very thermodynamic, that solves this problem and presents the theorem as a derivation, as an implication, as a consequence of the second law of thermodynamics. So I will first describe the traditional point of view of this problem. In the last section, I will present the proof, the new proof that I am presenting. So the Nernst theorem refers to the isothermal change of entropy. The isothermal change of entropy is the first input of the entropy, and it is just the ratio between the heat and the temperature of the process. The heat refers to the following. Think of a system, for instance, a gas or liquid, whichever system, and conduct a change in pressure, in volume, or in magnetic field, or in electric field. Well, usually the system will tend to change its temperature. The temperature of the system will naturally change usually. If this process is conducted, is carried out with the system in contact with a thermal bath, then the thermal bath will prevent the temperature from changing, and the system will do the equilibrium state of the system will perform a path where the temperature will not change. For that to occur, the thermal bath needs to exchange heat with the system, and the ratio between the heat exchanged needed to hold the temperature and the temperature of the process is the isothermal change of entropy. The Nernst theorem states that the isothermal change of entropy vanishes as the temperature vanishes. Now, if you look at the definition of isothermal change of entropy, we have here Q over T. If T goes to 0, then here the denominator goes to 0. We are dividing by 0. If the result is 0, it is necessary that this quantity, that the heat, also vanishes when the temperature goes to 0. So the following discussion will be pretty much related to the fact that these two quantities must go to 0 simultaneously. And we need to discuss how, because of course, the empirical evidence collected by Nernst is that this two quantity goes to 0 in a way that their ratio goes to 0 as well. The issue, the important question, is whether this equation 2, is derived from Planck's statement of the second law, or is it is a new independent postulate, a third law of thermodynamics. And the problem is pretty much related to the second law, because the Carnot engines, which are the most simple, the simplest engines we can run, also show the isothermal change of entropy. The Carnot engine just is an engine which is operating with two reservoirs. Extracts heat from a boiler temperature TB, and pours heat into a cooler, temperature TC. And the difference between the heat extracted from the boiler and poured into the cooler is the work. This work serves for a purpose. It is able to raise a weight, or it is able to move a car, or it is able to charge a mobile phone, or whatever, whichever. On the left side, we have a SD chart of this Carnot engine. And we have here the isothermal change of entropy. And here there is another isothermal change of entropy in the cooler. This is in the heater and in the boiler. And here we have the isothermal change of entropy in the cooler. So the area of this cycle is the work performed by the engine. And this work equals to delta S times delta T. And this is a consequence from the first law also. The second equation that is presented in this slide refers to the efficiency of the engine, the ratio between the work extracted by the engine and the heat extracted from the boiler. This ratio can be written in this way. This is related to the first law. I mean, this is only the first law. But the second law of thermodynamics writes this efficiency in this way. And this is known as with the name of Carnot's theorem. And all this is related to the statement of the second law, to Planck's statement of the second law. Planck's statement of the second law is saying, if a wave is rising, you need to heat a cooler. I mean, it is impossible to obtain some work without heating the cooler. A work without the cooler being heated is a negation of the statement of the second law. Planck's statement is saying, you rise a wave, you obtain a work, okay, you must heat the cooler. And the thing here is that if the temperature of the cooler goes to 0, then the heat in the cooler also goes to 0. And therefore we are in this scenario. We have QC to 0, and apparently if the work is positive, I mean, if we obtain work from this engine, then we will be negating Planck's statement of the second. But of course, on the second line, Nernst's theorem comes handy, because Nernst's theorem is saying Tc goes to 0, Qc goes to 0, and at the same time, Qc over Tc, I mean delta S, also goes to 0, and therefore the work is fading away as well. In the end, we have that when the temperature of the cooler goes to 0, this is wrong, I mean this cooler should be here at 0. When the temperature of the cooler goes to 0, on the one side we have that the efficiency of the engine is 100% efficient. The engine is super mega efficient. It is challenging Planck's statement of the second law, but the Nernst theorem is saying that the work is 0, and therefore the Nernst theorem is saving Planck's statement of the second law. This is not a proof of the theorem. This is just recalling or telling what the theorem is saying to us. Nonetheless, Nernst's proof of his theorem more or less ran in line with this argument. Nernst said the absolute 0 is unattainable, and this is a consequence of his theorem. I mean, the unattainability of the absolute 0 is a consequence of his theorem. And he said the absolute 0 is unattainable, must be unattainable, because otherwise a Carnot engine operating at T equals 0 would negate Planck's statement of the second law. Therefore, the empirical observation associated with the Nernst theorem are derived from the second law of thermodynamics. This is an argument. This was 1912. In the following year, during the Third Solvay Congress, Albert Einstein refuted the proof and said, even if a system at t equals 0 would exist, an engine operating at t equals 0 could not be run in practice. Therefore, it could not challenge Planck's statement of the second law. Consequently, the observations are an independent postulate and are supported only by evidence. Einstein pronounced the theorem a postulate, pronounced it the third law of thermodynamics. And because Einstein's argument was a bit more sound, and Einstein had a larger prevalence and a higher prestige at this moment, Einstein's point of view prevailed, with in time on the third law being sustained in time. Now, let's see my arguments, the new point of view. Well, Nernst was wrong with his proof, and the mistake by Nernst has been already presented. An engine operating at t equals 0 does not, of necessity, challenge the statement of the second law. If QC goes to 0, or if the efficiency of the engine goes to 0, this is not, of necessity, a negation of the statement. For a negation of the statement, we need work. If QC to 0 is accompanied, is followed by work going to 0, then the statement prevails. Einstein was wrong, well, because he didn't notice this argument, of course, but was wrong because Einstein was saying a Carnot engine operating at t equals 0 cannot run in practice. But the thing is that the second law demands that engines operating at t equals 0 must run. And this is because of a very curious argument. We usually see Carnot's theorem that way. I mean, it is relating the heat exchanged by the Carnot engine with the temperatures of the reservoirs. But strictly speaking, this equation 8, should be read all the way around. I mean, it is the temperature that is assigned by the heats exchanged with the cooler and the boiler. Think of the temperature of the cooler and the temperature of the boiler. You say, okay, the temperature of the cooler is at a lower temperature than the boiler. But this is because the heat exchanged by the cooler is always smaller than the heat extracted by the boiler. You extract a quantity from the boiler. This is the total thing. This is your amount of energy. And then you share this amount of energy with the work and with the cooler. The quantity poured into the cooler is smaller than the quantity extracted from the boiler because some amount is going to happen in the form of work. So therefore, these two heats are smaller than the unity. And as a consequence, the temperature of the cooler is smaller than the temperature of the boiler. So this is a consequence of the first law. This is not a prerequisite. We don't need to know preemptively that the cooler has a smaller temperature than the boiler. We obtain this as a result from the analysis, from the energetic analysis of the cooler. I mean, this is a thermometer. a universal thermometer. More than that, this is not really a thermometer. A thermometer is just measuring temperature with the helped by the length of a liquid or helped by the pressure of a gas or something like that. This is a definition of temperature. And the important thing in this discussion is that when we speak of T equals 0, in classical thermodynamics, we only mean that a reversible Carnot engine is able to establish that the temperature of the cooler is 0. How? Through equation 9. I repeat, the point is that assigning T equals 0 to a system, to a thermodynamical system, requires within classical thermodynamics that a reversible Carnot engine is able to establish this measure, the measure T equals 0. I mean, engines operating at T equals 0 must run, if only to measure T equals 0. There is no other way within classical thermodynamics. With that in mind, the proof is straightforward, because I just rearrange this equation to obtain this equation. Again, this is Carnot's theorem, and we have Tc equals 0, and therefore Qc equals 0. Now, equation 7 applies. If Qc goes to 0, then there must be no work in the engine, and therefore there should be no heat extracted from the boiler. This Qb equals 0. Finally, this Tb is non-zero. As a result, on the left side, I have 0 over non-zero. This is straightforwardly 0. On the right, I have 0 over 0. This is a forbidden operation by mathematics, but because of this equal sign, which is this equal sign, which is this equal sign, it's always the same equal sign. Because of this equal sign and because this quantity is 0, I know this quantity will be equal to 0. Therefore, Qc over Tc equals 0. But because Q over T is the change of isothermal entropy, we have arrived to the fact that the limit when the T equals 0 of delta S T equals 0, which is the Nernst theorem. We have proven the Nernst theorem from the Planck statement of the second law. In the end, what I am saying is that this null engine has just one purpose, the purpose of determining T equals 0. In fact, a system is at the temperature T equals 0 if the Carnot engine that attempts to measure the temperature provides no work of necessity. I mean, it is impossible to obtain work when we are trying to measure the temperature of this system. The null temperature is assessed by a null Carnot engine, and this is not strange. I mean, if you are trying to assess a null length or a null mass, you need a null measurement. You need a null device to make this null measurement. So this is the end of the talk. I just left here. I mean, I am just showing here a one-line proof of the theorem with the Carnot engine on display. If Tc goes to 0, then Qc goes to 0. And therefore, by means of the Planck's statement of the second law, this work must go to 0. Conservation of energy makes this Qb go to 0. And because Tb is non-zero, Qb over Tb will be 0. I am just here, so I am just making this material implication. Finally, applying Carnot's theorem, Qc over Tc also goes to 0. And finally, applying Clausius' theorem, which is the definition of entropy, we arrive to the final answer. Delta S goes to 0 when T goes to 0. there is a final nuance in the last step of the proof. And the thing is that here, these quantities, all this quantity refers to properties of the engine. It is this QB, this QC, this TC, this TB, all this work, all this, the quantities of the engine are collected in these material implications. Now, the last step refers to properties of the system undergoing the cycle. It refers to the fact that the charge, the entropy versus temperature charge of any substance must end in this tiny point. A point, a final point here. I think I have forgotten to speak about that. This implication, it is universal. This is fulfilled by any thermodynamic system, because this equation, Carnot's theorem, is also universal. Any substance in the nature is suitable to perform this Carnot engine that attempts to measure t equals 0. So this Carnot engine, which is of course narrowed to a strip, is independent of the system that is undergoing the cycle. All the systems, all the Carnot engines that attempt to measure this t equals 0 would behave in the same way. So that's the proof. This is the one-line proof of the Nernst theorem. I hope you have enjoyed this talk. Spread the word. Have a nice day. Here there are a few references, classical references on this field, as Carnot, on Nernst, Planck, on the proceedings of the Third Solvay Congress. These slides are available at Zenodo under this DOI. Have a nice day, and many thanks. Thank you so much for your kind attention.